This is our problem session 11, and we shall solve minor 3 problems and a couple of problems on widebanding by compound devices if time permits. The first problem in minor 3 was to determine the low frequency 3 dB cutoff, FN, and the circuit given is this: 500 ohm, 10 microfarad. Let's call this as C1. Identify this as C1. This we identify as RS. We give a name. The current I sub C is given as 1 milliampere and beta is given as 20 intentionally. I was asked a few questions whether this is a printing mistake or not. And also someone asked me, how do I find GM? You have not given GM, you have not given R pi. I smiled. 10 microfarad, we call this as C2 and 1K. This is my output voltage V0. Biasing details are omitted. That's why only this current is given. If this current is given, now I think as far as finding the parameters are concerned, that's very simple. GM would be 1 by 25 mho and R pi would be 500 ohms. 20 divided by 1 by 25, so 500 ohms. See, I chose these numbers intentionally so that the answer comes as a very nice figure, so that you don't have to spend time on cranking figures, numbers. Okay. Then the question is, you have to decide what method you shall apply. Now, if you draw the equivalent circuit, the choice should be obvious, whether you do an exact analysis or the method of short circuit. Short circuit or open circuit here? Short circuit time constant. This decision will be based on how complicated the equivalent circuit is. If the equivalent circuit is complicated, then you take a shortcut to the short circuit through the short circuit time constant method. If it is not, then you better do it exact analysis. Now, it turns out that the exact analysis is involved in this case. If you draw the equivalent circuit, well, I did draw it, and if one tries to solve it, then immediately it should be obvious. Well, we can draw it as well. This is C1 and then R pi, no C pi, because we are doing the low frequency. Okay, so this is V pi, this is C1 RS, Vs, then this goes to Re, which is 1K, and there is a GM V pi. This goes to ground, and then you have the C2 and RL, let's say, which is 1K. This is V0. Now, obviously, it's not a very simple analysis. It cannot be done, can be done by inspection, but the expression that you will get will have zeros as well as poles. Not only that, inspection also requires a little bit of ingenuity, because the equivalent impedance here is not simply Re parallel RL. It is Re parallel 1 by SC2 plus RL, and that's how you will be able to find out V pi and then find V0 as potential division between the two. Not that it cannot be done, but it will require detailed calculations and it will require time. So, we offer the short circuit. We offer a short circuit through short circuit time constants. As I said, we first find out, as far as as far as the equivalent impedance seen by C1 is concerned, R1 would be simply, this will be grounded. You can do it by inspection. This will be grounded. This is R pi, and the equivalent impedance here would be beta plus 1 Re parallel RL. So, it can be written down by inspection: Rs plus R pi plus beta plus 1 Re parallel RL. Now, you see how I chose the numbers. Both of these are 500. This is 500. This is 21 times 500. So this is 23 times 500 ohms, which is equal to 23 by 2K. Okay, 23 by 2K. All right. Now let's look at the look at what C2 sees. C2 sees some tricks of the trade. This can also be done by inspection. You see, C2 sees this circuit. There is an RL here, which is 1K. Then it sees an R pi, no, RE. RE. Don't draw GMV pi here. Okay, draw GMV pi like this. Don't draw it upstairs. Draw it as GMV pi. Is the direction correct? Okay. Then you have R pi and series RS that goes to ground, and there is a V pi voltage here with this polarity, plus minus. Okay. And this is the impedance. Well, you connect a voltage source V here, any polarity doesn't matter, and this is the current I. Now, what you should do before writing any loop equation or node equation, you should observe that RL is in series with the source. Therefore, whatever impedance it sees, R2 shall have RL in series. Isn't that right? So you can ignore this now. You can find out the impedance of the rest. Now, impedance of the rest obviously has RE in parallel with something. Okay, so plus RE parallel. Therefore, all that you have to find out is the impedance looking back here, a GM V pi, V pi, and RS. Agreed? And that we have found out again and again and again. This is obviously R pi plus RS divided by beta plus 1. Agreed. And this, my calculation, I don't know what yours is, it comes out as 23 by 22K. Both of them have 23. I chose this intentionally. Therefore, R1 parallel R2, which we shall get later. Can you tell me how much is this? 23 by, is it 23 by 24 or 24 by 23? 23 by 24. Agreed? 22 by 23, 22 by, so 20. Okay, so much of K. We will require this later. You cannot anticipate this right away, but you can as well, because FL is 1 over 2 pi, 1 over 2 pi, 1 by tau 1 plus 1 by tau 2. Isn't that right? Have I done it correctly? Because 1 by tau is equal to 1 by tau 1 plus 1 by tau 2. And 1 by tau is 2 pi. This is correct. This is also correct. This is also correct. I have not made a mistake so far. Okay. And since the capacitors are equal, you get 2 pi C 1 by R1 plus 1 by R2. And that's how you get 1 by 2 pi C R1 parallel R2. This is what I said. We required this. If you substitute these values and do the numerical calculation, well, you get 2 pi C is 10 microfarad, 10 times 10 to the minus 6, and R1 parallel R2 is 23 by 24. So let's say 24 K, and therefore this should be multiplied by 10 to the 3. So many hards, and this finally you will have to apply your calculator because of division by pi. Otherwise I can do it almost mentally. It's 16.6 hards. That's the value. Let's look at the next problem, problem number 2. Any question on this? Any question? Okay. Problem 2 is a feedback circuit. With a BiFET feedback circuit. BiFET means BJT and FET combination. Okay, this is quite common. BiCMOS technology, for example, is a very popular technology. And for different reasons this is used. For example, if you have a source which is not too low an impedance, a microphone for example, it is better to put it at the input of an FET, because FET has a very high impedance, input impedance. On the other hand, the high frequency response of a BJT in the common base connection, for example, is much higher than that of a FET, and therefore one makes combinations to get the best of both worlds. This is one such circuit. However, I didn't give numerical values so that you don't lose your patience in numerical calculations. This is my Q1, and there is a resistance R sigma through which there is feedback. This is brought to a PNP transistor, which the emitter is connected to the positive supply plus VDD or VCC, VEE, whatever you call. Then you have an R sub C, and this is connected here. There are two voltages which are taken. One is here V02 and the other is here V01. Okay. The first thing, this is Q2. And the question was to apply feedback methods to find out V02 by Vs and V01 by Vs, both of them. Okay. Now obviously several people asked me, suppose I find one of them and then apply potential division. Obviously that is not correct, because potential division shall occur only when the same current flows through both the circuits, both the impedances. It doesn't, because what flows to RC also flows to R sigma, but R sigma also carries a current from Q1, and therefore potential division is not applicable. And in fact the beta is different for both the circuits. The gain is different, and therefore there is no way you can derive one from the other. You have to do it independently. And the first thing, the simpler of the two would be to consider V01 as the output, and it is obvious that it is a voltage sampling. It's a shunt connection at the output and a series connection at the input. So it's a series shunt. That applies to both V01 and V02, both of them. So if we consider V0 as V01, then my equivalent circuit would be Vs that's it, this is the gate. Now the source, if V01 is short circuited, obviously this will be shorted, and therefore the source is shorted, S is shorted, and what you have here is GM1 VGS, and VGS would be equal to Vs. Intentionally I put this symbol as Vs because you might get trapped in the next question where there is a potential at the source. You could call that V sigma. Okay. GM1, don't get confused over these minor confusions, humanly created minor confusions. Well, confusions always are humanly created. Nature doesn't create confusion. Okay, this is the drain, and then the drain of the first transistor is connected to ground through a parallel combination of RD and R pi 2. If you look at this, RD, that goes to ground, and from base to emitter is R pi 2. Several people asked me whether the polarity in the equivalent circuit changes, whether it's a PNP or NPN transistor. And one of them I scolded, the other one I simply smiled, because there is no point in scolding, and the smile should clarify the answer. Okay, so this would be RD parallel R pi 2. We call this as R pi prime, let's say. Okay, and this voltage is V pi. Then you have a GM2 V pi, GM2 V pi, that goes to ground, and what you have here is RC, then you have to open this because it's a series connection. So RC plus R sigma. RC plus R sigma, and the voltage is taken from here. Now, I have repeatedly told you that please do exercise some discipline, otherwise you get confused. This should not be called V01, V01 prime, because this is the A circuit. This is not the total circuit, this is the A circuit, and the gain A can be very easily found out. V01 prime by Vs, this is equal to minus Gm2 times R sigma. Okay, this current flows through this, so it's independent of RC, minus Gm2 R sigma, and then V pi would be minus Gm1 R pi prime. Okay, and that's it, because this Vs is the same as the input Vs, and therefore this is equal to Gm1 Gm2 R sigma R pi prime. Now, the calculation of beta, does not require an equivalent circuit, because all you have to do is to apply voltage here, open this and find the voltage here. Obviously beta is equal to 1, therefore beta equal to 1. Someone asked me whether he should leave it like this or he should find out AF, the feedback gain. This is V01 divided by Vs. Well, why this laziness at the last point? If you have been able to find this out, you could as well find this out. Now, does this surprise you that the gain is less than 1? No? I wonder why not. Why not? If you look at this circuit, does it surprise you that the gain is less than 1? V01. Okay, obviously it is the voltage between the source voltage divided by the generator voltage. Okay, this is like if the feedback was not there, if this was not there, the gain obviously would be less than 1, because it behaves as a source follower. Whether there is a resistance here or not, it doesn't matter. Okay, it behaves as a source follower. So the gain is indeed less than 1. All right. As far as if V0 is V02, then the A circuit changes slightly. What you get is Vs G. Now S is no longer grounded. Okay, S is no longer grounded. S is grounded through a resistance of R sigma parallel RC. Why this parallel comes? Because V02 is now to be grounded. Okay, V02. If you look at this circuit, it is this point which is to be grounded, and therefore R sigma comes in parallel with RC. And the rest of the circuit is very similar. GM, now VGS obviously would be, we'll have to find that out. Okay, we'll have to find that out. So let's be content with GM VGS. Then you have R pi prime, V pi, and you have GM2 V pi. The rest of the circuit is similar. What shall you have here now? RC plus RL. You don't have to show them separately, because V02 prime is here. So this is RC plus RL. And all that you have to do now, pardon me? RC plus R sigma. That is, thank you. RC plus R sigma. All you have to do now is to show, is to see that VGS is equal to Vs minus the drop in this, which is GM VGS R sigma parallel RC. And therefore you can find out VGS. If you can find out VGS, you can find out A. And you can find out A. My result is the following. GM1 R pi prime, GM2, instead of RC, you have RC plus R sigma, divided by 1 plus GM1. Where does this factor come from? This factor 1 plus GM1 R sigma parallel RC, where does it come from? VGS, from the calculation of VGS. Okay, this is A, and beta obviously here is a potential division, that is R sigma divided by R sigma plus RC. Does that require explanation? The circuit itself shows that, and therefore AF, let me now be as lazy as the person who asked me whether he should find this out or not. Please do. Question number 3. Here I had a barrage of questions in the class. Let me tell you what these questions are. Once again, this is a BiFET circuit. That is, there are FETs and a BJT. This is V1. It's a differential amplifier, 20K. This is also 20K, absolutely symmetrical. This is Q2, Q1, and this is V2. The two sources are brought together and biased through. Which kind of source is this? Current source of the Widler kind. Okay, this is 500 ohm, and then it goes to minus VEE. But these 2 points, the base, well, is connected to the power supply through a resistance which is not given, and then you have a Zener diode, and it is given that 1.2 volt Zener. Okay, this is the circuit. So people ask me, what is VCC? What is VCC? What is this resistance? What is VEE? If you, this is called what? Seeing? No, not seeing, observing. If you observe carefully, this 1.2 volt Zener, there is a purpose. A Zener stabilizes voltage, and therefore the voltage that will, and it's in the reverse direction. So Zener breakdown occurs. There is a plus VCC. This resistance has been chosen such that VCC plus VEE, this voltage is greater than 1.2, agreed, and this resistance is chosen such that the breakdown occurs and the voltage is maintained a constant. Okay, which means that this voltage from here to here is 1.2 with this polarity. If that is so, and if this is 1.2, obviously Q3 shall be in the active region. This question was also asked. Why is Q3 in the active region? Well, Q3 requires 0.7 and it's greater than 0.7, therefore it must be active, and this voltage must be 0.7 plus minus, and therefore this voltage, now look at my choice, this voltage must be 0.5 volt, and therefore the current through this must be 1 milliampere. All right, and this current, therefore, since this circuit is symmetrical, this current must be 0.5 milliampere, this current must be 0.5 milliampere. Everything else is known. For Q1 and Q2, the further specifications are that IDSS equals to 3 milliampere, VP equal to minus 3 volt. Now, why are these given? Because we require a calculation of GM. Okay, so GM1 or GM2. Now, some of you, I have seen a few papers, some of you first calculated VGS and then substituted in the formula for GM. But we had made a shortcut. What was it? IDSS divided by minus 2 by VP square root of IDSS IDQ. And VP is known, IDSS is known, IDQ is known. IDQ is 0.5 milliampere, and therefore GM can be found out. What else is required to be found out? RD, and I have given you equivalent VA. Equivalent VA. I didn't want to use the symbol lambda inverse because you may not remember. I mentioned it only once in a class. So equivalent VA is given, therefore it should be 100 divided by 0.5, which is equal to 200 K, 200K. That's right. So you know GM and RD, and if you know GM and RD, then the differential gain is immediately found out, minus GM times RD parallel small RD, and this is 20K and this is 200K. GM is known, and therefore you can find out the gain. As far as the CMRR is concerned, now you have to take help of Q3. CMRR is determined by the equivalent resistance that is presented between these 2 points. If we call this R0, then the CMRR shall be determined by one plus GM 1 or 2 or 3, 2 or 1, it doesn't matter because they are identical. Okay, so GM 1 R0. That's it. Twice GM 1 R0. Okay, that's right. Twice GM REE, equivalent resistance. All right, and R0 is this we have done for the Widler source. It would be R03 1 plus GM3 pardon me? Okay, RE3 parallel R pi 3, right? This parallel comes, usually R pi 3 is much larger than RE3. In fact, this is the case here also. What is R pi 3? Pardon me? 500 ohms.
5K, sir. 5 kilo ohms.
Oh, 5K. And RE3 is 0.5K. So this is 10 times. Agree? This is usually the case. And you could as well ignore R pi 3. But R03 is how much? Again, VA is given 100K. And GM is again 1 milliampere is the current, and therefore 1 by 25 mho. Substitute all this and get this as approximately 2100K. And therefore, the CMRR, if you substitute the numerical values, CMRR is equal to 34, this is my result, 30.3 and it is always a practice for engineers to specify this in dB. If you specify this in dB, what do you have to do? You take log 10, 20 or 10? 20. Okay. Why? Because it's a ratio of 2 voltage gains. Okay. This, my calculation says this is 70.7 dB. And the differential gain is equal to minus 14.85. Would you also like to express this in dB? Why not? It's very low, 14.85. Not only that, if you express in dB, then you must take care of the negative sign. How do you do that? You see, dB you cannot take log of a negative quantity. You take the mod, you either express AD as mod, so many dBs, or you say AD equal to so many dB, then angle pi. Okay? Don't say minus so many dBs. No, that doesn't make sense. Okay? Minus so many dBs means what? That means attenuation. We always say minus 3 dB frequency. Alright? The attenuation is 3 dB. Okay. These are things that an engineer should remember. Now in the rest of the time, we will work out 2 examples of broadbanding by compound devices. The first example is that of a cascode. This page is not sufficient, so let's draw it on a separate page. This circuit, draw with me, plus 10 volt, R sub C equal to 5K. You have the transistor Q2 the base is maintained at a constant voltage of 1 volt. Okay, the base biasing is not shown, it's maintained at a voltage of 1 volt. Perhaps a 7.2 volt Zener and then a potential division, perhaps of that type. Okay, we don't get a 1 volt Zener. 7 is perhaps the minimum. No, there are smaller voltages also. Pardon me? 3 point? 5.6 is there, yeah. 5.6, 6.2. Do you know the logic of these fractions? Why 4.7K? Why not 4.8? You better find out. You better find out. The processing facilitates manufacture of such values, and this has become almost standard. Look at any components handbook in the library. I don't want to give you the answer. You will find out for yourself why these specific values. 3.3 microfarad, not 3.21 or 3 microfarad. No. Okay. Q2. Then you have a Q1, and the biasing here is that a constant current source I equal to 1 milliampere. That means another transistor, either a Widler source or an ordinary source, okay, which can be approximated by an ideal current source. We consider its equivalent resistance to be infinity. But then for AC it would be open, and therefore I make an AC short by connecting a capacitor to ground where this capacitor is very large. You understand the meaning of this? Why this is done? Ideal current source, but I want Q1 emitter to be grounded as far as AC is concerned. If I don't use this capacitor, then it will be open, it will not be grounded, and therefore AC will not be able to flow. Therefore I provide a short circuit for AC here. This does not affect the DC, and the source is applied here, RS. This is my Vs. The transistors, both of them have a beta equal to 100. Obviously they carry the same collector current, so GM1 and GM2 are equal, and that is what gives the cascode its basic property, namely that it can extend the high frequency range. Beta is 100, C pi is given as 5 puff, and C mu is given as 1 puff. The question is to find out, let's see if there is anything else. No, the output is here, V0, as usual, it's a cascode. The question is to find out the pole frequencies, and estimate FH for two conditions, RS equal to 1K and the other is RS equal to 10K. There must be a difference, that's what. Alright, have you been able to draw? Okay. Since the current is given as 1 milliampere, our GMs are obvious. GM would be equal to 1 by 25 mho, and therefore R pi would be equal to beta divided by 1 by 25, that is equal to 2.5K. Then instead of drawing the equivalent circuit, let's see if we can do it by inspection. Okay, the equivalent circuit, as you remember, is fairly complicated, and then there was a current generator which had to be taken care of in two parts through a resistance 1 by GM2 and a current generator GM2 V pi 2. Let's see if we remember little bit of the equivalent circuit, whether we can do it by inspection. Let's look at this. First, let's consider the output circuit. The output circuit time constant, or the pole frequency, which let's call as F3. Who determines this? Obviously RC. Does RC come in parallel to anything? No. And the capacitor is from here to ground, that is C mu 3. Anything else? No. So F3 is simply 1 over 2 pi RC C mu 3, and if you substitute the values, this comes as 31.8 megahertz without drawing an equivalent circuit. Okay. All right. Then the second one, that is F2. F2 would be at this point. F2 would be determined by the time constant at this point, that is E2. Pardon me? I'm sorry, C mu 2. I beg your pardon. C mu 2, which is 1 puff. 1 puff, okay. Now let's see F2. Tell me what is the equivalent resistance at the emitter of Q2. And since beta is large, this is approximately 1 by GM2. Agreed? This is what gave the widebanding property. Because the load is 1 by GM2, the gain is equal to minus 1. GM1 multiplied by 1 by GM2. If you remember this property of cascode, then you don't have to draw the equivalent circuit. So what we have is 2 pi. Let's say this is approximate. I'll tell you how good this approximation is in a moment. 2 pi 1 by GM2, and what is the total capacitance? C pi 2 not plus twice C mu 1, because the gain was equal to minus 1. This is C mu 1 multiplied by 1 minus gain divided by gain magnitude. So 1 minus minus 1. All right. And if you substitute the values, then this comes out as 0.97 gigahertz. How many megahertz it is? 970 megahertz. 970 megahertz. Now let's see how approximate this is. You see, actually this resistance should be R01 parallel R pi 2 parallel 1 by GM2. R01 VA is not given, so we assume this as infinity. R pi 2 is 2.5 K, and what is GM2? 1 by GM2? 25 ohms, which is 0.025 K. Don't you see that this dominates? 1 by GM2 dominates. So this result, I can as well remove this hesitation. Okay? It's almost exact. Right. Now, finally, our F1, the corner frequency F1, the pole frequency F1. This is due to the input circuit. Let's look at the input circuit. Input circuit, what is the equivalent capacitance from here to ground? C pi 1 would not have been there unless this. Okay, so C pi, only C pi 1? No. Plus twice C mu 1. What about the reflected? And what is the equivalent resistance? RS parallel R pi. That's correct. And therefore I didn't have to draw any equivalent circuit. F1 is 1 over 2 pi R pi parallel RS multiplied by C pi 1 plus twice C mu 1. This is 5 puff. This is 1 puff. So 5 plus 2 is 7. 7 times 10 to the minus 12. And R pi parallel RS. R pi is 2.5 K. RS is 1 K multiplied by 2 pi. So this is what I get, F1. And by calculation I get this as, if RS is 1 K, then I get this as 31.7 megahertz. Whereas if RS is 10 K, I have been asked to calculate for two situations. RS is 10 K, then this is 11.3 megahertz. If RS is 10 K, it's very tempting to divide this by 10. That is not correct, because there is a parallel combination. Okay, let's consolidate the results. My F1 is either 31.7 or 11.3 megahertz. F2, what was the value? 970 megahertz. And F3 is 31.8 megahertz. Now, if I want to calculate exactly, obviously you see the effect of F2 would be negligible because it is about 30 times the higher values, 30 times, it's approximately, right? So this effect would be negligible. Therefore, FH would be mostly determined by F1 and F2. In the first case, that is when RS is 1K, 31.7 and 31.8, they are comparable. And therefore, FH should be determined as 1 by square root of, can you tell me what should this value be? F1 squared plus F2 squared? No. 1 upon F1 squared. You must remember the tau's add. Okay, 1 by F1 squared plus 1 by F3 squared. You can as well ignore this. And in the first case, that is when RS is 1K, they are comparable, and the result is 22.5 megahertz. Whereas if RS is 10K, then it should be approximately 11.3, because this is also 3 times now. Okay, and the exact value is 10.6 megahertz. Slightly less than this, slightly less than 11.3. Okay, any question? The second problem. Second problem is that of a CCCE combination. Draw this circuit with me. Vs 10K, Q1, all transistors are biased by a current generator. This is biased by a current generator, and this goes to the next stage, that is Q2. This is also biased by a current generator, 0.5 milliampere. And then you have, in order that this is not floating, you apply a capacitance, a short circuit, a bypass capacitance. Yes.
Please show the previous slide for a second.
Previous, okay.
Now, sir, in this we have added the reciprocals of the squares of the frequencies,
Mhm.
then evaluated that expression to get effect.
Mhm.
Now, since the time constants add, and the inverse of the time constant, that is that of frequency.
Very good question. You see, what we have is tau equals to tau 1 plus tau 3. How come we took this 1 by f1 squared? Why did we take this square? This is more exact because 1 by fh square is equal to summation 1 by fi square. If I take the expression as 1 plus s by omega 1, 1 plus s by omega 2 and so on, I showed this, that in the magnitude squared, if you ignore omega h to the fourth and other terms, only keep the squared terms, then this is a better formula than summation of the time constants. This is not the method of short circuit time constant. It's a better formula. Okay, but even if you do it by this, it won't be much different. As I said, the estimates are fairly close to each other. Good question. Now, in this circuit, question number 1, I have not finished it, but let me raise some queries. Question 1, if both are both are biased by two constant current sources. Why couldn't you have a single constant current source of 1 milliampere and connect them? Pardon me? That's right. One is grounded and the other is open. This emitter current, AC emitter current, has to go to as base current of Q2. And therefore we could not make them, we could not short them. All right. Then Q2 is connected to a 10K resistance and the voltage here is plus 20 volt. The voltage here is plus 5 volt. Why is there a difference? This is V0. Why is there a difference? Come on. The question is, why is there a difference of power supply? I sub C's are the same. One at a time. Yes.
To get the proper VC, because the resistance of RC, the drop across the VC will be the same.
The VC here does not matter, almost doesn't matter, whereas it matters here. Isn't that right?
Sir, the IC of Q2 will be greater than the IC of Q1, so by factor of beta.
But beta is large. Beta is 100. So that can be ignored. Think about it. I have given the answer. Think why this answer is correct. If it is not correct, then counter me. The other specifications are this: beta equal to 100, C mu equal to 2 puff, and Ft. Instead of being given C pi, now you are smart, you can calculate C pi, right? Tell me how you calculate C pi. It's equal to Gm, pardon me, Gm by 2 pi Ft minus C mu. Therefore, C mu is given and therefore you can calculate C pi. Alright. The question is to find out the mid-band gain and FH. These are the things to be found out. Mid-band gain and FH. We could do that by without drawing the equivalent circuit. Also, if we recall a bit of the equivalent circuit, but let's do it because we have to calculate the mid-band gain also. Let's draw the equivalent circuit. It doesn't take much time. Vs, Rs, which is 10K. Then what do you have from here to ground? From here to ground, what do you have? If you look at the equivalent circuit, R pi, not to ground. To ground, I am asking to ground. Is there any element? C mu 1, that is correct. C mu 1. And then you have R pi 1 parallel C pi 1. This is V pi 1. This goes to R pi 2 parallel C pi 2. And there would be a current source here, Gm1 V pi 1 coming from ground to here, and then from here you get a C mu 2, this voltage is V pi 2, C mu 2, then what? Gm2 V pi 2 and RL. This is V0. Is the equivalent circuit. You should not spend much time in drawing the equivalent circuit. It should be, looking at the circuit, it should be obvious. Now, the easiest thing to find is the mid-band gain. Mid-band gain. Mid-band gain. Okay. Obviously, this would be minus Gm2RL for this stage, then V pi 2 divided by Vs. Agreed? This voltage is minus Gm2 V pi 2 RL. Ignore all the capacitances, mid band, and then you have to find V pi 2 in terms of Vs. Therefore, it would be minus GM2 RL. What is V pi 2 by Vs? Beta plus 1 R pi 2 divided by beta plus 1 R pi 2 plus Rs R pi. Very good. By inspection, no analysis, nothing. And if I substituted the values and I find the result as minus 194. Obviously, because I sub c's are the same, GMs are the same. That's why I didn't make a difference between beta 1, beta 2, R pi 1, R pi 2. They are all identical because I sub c's are equal. Okay. Now about the time constants. Again, now we don't look at the, since we have taken the trouble of drawing the equivalent circuit, let's look at the equivalent circuit and find out the equivalent resistances. But before that, shall we take help of Miller in getting rid of this? So this shall be multiplied by, this should be added to C mu 2 1 plus GMRL, and instead of RL we shall have here a capacitance of C mu 2. Agreed? Then how many capacitors we have? 1, 2, 3 and 4. 4 capacitances. So we have to find the equivalent 4 resistances. Let's see if we can do it by inspection. Okay. What does C mu 1 see? It sees a parallel combination of Rs and R in, not R pi 1. R pi 1 plus beta plus 1 R pi 2. So you can find out R mu 1. What about CT2? What about CT2? Well, what about RT2? What does this see? Obviously it will be a parallel combination of R pi 2. Wonderful. So R pi 2 parallel R pi 1 plus Rs divided by 1 plus beta. And this comes out as 144 ohms, my calculation. R pi 1, we jumped from here. Now R pi 1, that is C pi 1. What does it see? R pi 1 parallel, Rs is here and R pi 2 is here. Okay. This would be R pi 1 parallel, not beta plus 1. Yes, correct. Rs plus R pi 2 divided by beta plus 1. Agreed. This also comes as 144 ohms. Why? Because they are identical. R pi 2, R pi 1, R pi 2, R pi 1. They are identical. So this is also the same. And finally, R mu 2 is simply no, Rs plus R pi 2. Why? You see, what does C pi 1 see? R pi 1, there is an Rs here and there is an R pi 2 here.
So beta plus 1 current is only flowing through R pi 2.
Actually, it is 1 plus Gm times R pi 2. 1 plus Gm, we calculate it out. It comes out as this. R mu 2 obviously is equal to 10K. And my time constants, tau, pardon me? 1 plus R mu 1. What was R mu 1? Did we not calculate this? R mu 1, yes. I have calculated, I will give you the value. R mu 1 is 9.81 K. And tau is equal to tau mu 1, tau pi 1, tau t plus tau mu 2. And my calculation says this is 19.62, all in nanoseconds. 0.86, 58.75 and 20. You see, none of them are really dominant. These two are comparable. This is approximately 3 times, so you can say this is dominant, but the two together makes its dominance disappear. Isn't that right? Yes. So I can't say 58.75 is dominant, but 0.86 perhaps we can safely ignore. You see, it is the time constant due to C pi 1. C pi 1 otherwise creates havoc because of Miller effect. But because Miller effect only reflects 2 C mu 1, nothing more, this has become very negligible. And my calculation is that tau, total tau is 99.2 nanosecond, and FH, which is 1 by 2 pi tau. Now we did not apply that squared formula. Okay, we could have done that also. We could have done that, but we found this to be more convenient. So we say this is equal to 1.6 megahertz. Okay, that's all for today.